Today's lesson, we're going to just continue the metal extraction for the AQA students by looking at how to extract copper. So in the previous lessons, we covered how to extract metals. So we said if a metal is more reactive than carbon, you must use electrolysis. If a metal is less reactive than carbon, then you can use a displacement or reduction reaction using carbon. And then we had the exception of tungsten. Okay, tungsten, which you had to use hydrogen to displace it, because the tungsten and the carbon, the tungsten and the carbon can react to form tungsten carbide. Okay, so we need to watch out for that. So carbon plus tungsten oxide can form tungsten carbide, sorry. So that's why we avoid that, and we do hydrogen plus tungsten oxide to make tungsten plus T. Now, the most reactive metals electrolysis, we've done how to extract aluminium in the industrial electrolysis section. So now we look at copper-rich ores. So how to extract copper? Well, we have different methods depending on if we're using a copper-rich ore or a not copper-rich ore. So a copper-rich ore is one which contains a high percentage of copper. And an ore is defined as a mineral or rock that will contain the copper in this case. Now, obviously, there's a finite number of rocks, so it can run out. The traditional methods include digging. So you dig it and extract the rock from the ground. You transport it to where you're going to process it. And when you process it, you get a lot of waste rock being disposed of. Now, how to actually extract the copper? How do you get the copper metal out of the ore? Now, the copper ore essentially is copper oxide. It contains a lot of copper oxide. So in one method, you could add sulfuric acid to it directly to form a copper sulfate solution. And once you form your copper sulfate solution, you could perform your electrolysis to it, and you'll get copper and oxygen on each electrode. The second method is called smelting or roasting. So you take your copper oxide, and you heat it to a high temperature, and you end up making an impure copper. Okay. Now your impure copper is put as the positive electrode. On the negative electrode, you would have to have some initial pure copper for this to work. So you put some pure copper on the negative electrode. What will happen over time? Oh, and the electrolyte has to be something containing copper. So for example, copper sulfate solution, aqueous. Now, what happens over time is that the copper atoms on the impure one get oxidized, so Cu. They lose electrons, which will flow across in the wire, and it'll become Cu2 plus 2e minus, an oxidation reaction at the anode. Like always is, anode is always oxidation in electrolysis. The electrons will float across to this side. Because the copper has turned to ions, the Cu2 plus ions in the solution will attract to the negative electrode. And then the electrons will come in here. So the Cu2 plus will gain the electrons that the other impure copper lost, and it will reform Cu. But this time the Cu will be very pure, and it will drop down here as a deposit, which you can then filter off. So it may seem a little confusing, but it's actually the same equation reversed. The main things are that you use a copper sulfate solution. You first smelt or roast your copper ore by heating it in a high temperature. And then you put your impure copper on the positive electrode and some pure copper on the negative electrode, and then you'll get a huge amount of pure copper being formed. Whatever mass is lost on this side will be gained here due to the conservation of mass. And that's all there is to it, okay? So in summary, metal ions are positively charged to attract the negative charged electrode, which is the cathode. The electrolyte must be a solution containing copper ions, so copper sulfate or copper chloride. Otherwise, other metals will form that can attract to the negative electrode. Impurities in the copper restricted the movement of the electrons, and therefore it doesn't conduct so well. So we don't want to use impure copper for wires, for example, because impurities will restrict movement of the electrons. Okay, that's why alloys will conduct less readily, for example. because the layer structure is disrupted and it's harder for the delocalized electrons to move through it. Now, that was what copper-rich ores. If we look at low-grade copper ores, so low-grade copper ores contain only a small percentage of copper. There's no point to apply all this energy for electrolysis, okay? And there's no point to apply all this energy for heating it and roasting it. So what you do instead is you have two methods. One is called phytomining. The other is called bioleaching. So if we start with phytomining, remember P for plants, B for bacteria. Ignore that it says plants here. It should just be bacteria, B for bacteria. So let's start with phytomining. What you do is you find some soil that contains a lot of copper ions in it or copper compounds. Obviously not the pure metal because you're trying to extract the pure metal. You plant these plants on top and they're grown on that soil. What the plants will do is they will absorb the copper ions through their roots. And the copper ions will go into the plant. Don't say the copper goes into the plant, because obviously plants don't absorb metals. The copper ions go into the plants. Now, the plants will then be burnt, okay? And the plant will turn into ash on top of the soil. What you then do is you leach the ash, you leach the ions from the ash by adding sulfuric acid to make copper sulfate. And then you have an option. You can either use a displacement reaction using scrap iron, so copper sulfate plus iron makes iron sulfate plus copper, or you could use the electrolysis method to make really pure copper, because you take a copper sulfate and you electrolyze it. So those are your kind of options. So in summary, you grow some plants that absorb the copper ions through their roots, you burn them to ash, you leach them by adding sulfuric acid, then you either do displacement using scrap iron or electrolysis. Now, bioleaching is the same thing but with bacteria. So you put some bacteria to feed on the low-grade metal ores. So you mix them together. Then, by combining biological and chemical processes and adding sulfuric acid, you leach once again the copper ions by forming copper sulfate. And then you either use scrap iron or electrolysis to extract your copper. So it's a very, very similar answer. The only difference being that you're using bacteria, not plants. 20% of copper comes from bioleaching, and hopefully that increases because copper-rich ores are going to run out. However, you should be aware of some of the pros and cons in these methods. So bioleaching is very slow, and so is phytomining, because you've got to grow the plants. And it'll take many years to extract just 50% of the metal. So here are some comparisons of the phytomining or bioleaching versus the traditional electrolysis method. The advantage is that you can extract copper from places where normally you wouldn't be able to, so low-grade copper ores. It requires less energy, less air pollution, and less waste rock. The disadvantage, it's much slower. It still needs some electrolysis at the end to purify the metal, which is expensive. And also, it can actually produce toxic chemicals, the phytomining and bioleaching, which could then damage further plants in the soil. Here are some more common questions and answers for this. So outline the process of phytomining, grow plants on low-grade ore, burn them to ash, and then it should say add sulfuric acid to leach the copper ions and extract using electrolysis. You will see some examples of this in some exam questions that have nice kind of summary answers for it. So that completes the lesson on copper extraction. So read up on it and just learn for 3 marks how to answer a question on bioleaching or phytomining, essentially. And the traditional method as well, which is when you have a high-grade ore, you smelt it, then you do electrolysis. And learn this type of electrolysis, yes? So where you have the decrease in mass here and the increase in mass here with the 2 half equations. because it's an unusual electrolysis. You're using copper metals as the electrodes, not graphite. Okay, so that's the end of this lesson. Take care and practice the worksheets attached.